Good evening to all of you. Hope you are all fine at your places. Today I am here with you one more video that is related to the design of synchronous machine, and this video is basically the continuation part of the previous video where we are discussing about the main dimensions, how the main dimensions of a synchronous machine can be calculated. We are dealing with the armature design, how the armature slots can be calculated. After that, we are dealing with the length of air gap. What is length of air gap? On which factors this length of air gap dependent? And what are the various factors from which we can calculate the length of air gap? So this is all we have covered in your previous video. Now today I am come with the continuation part in which we are discussing about some slot dimensions, how the slots can be calculated and how the slots area can be calculated in case of a synchronous machines, on which factor these slots can dependent. We are earlier we are dealing with the armature design. Here we are discussing about the number of conductors, total number of conductors per slot. Now in this video we are try to be understand what is the cross sectional area of the conductor that we can use in the armature winding, and many more. I hope you will watch this video carefully, and after this watching this video, all your doubts or the concepts related to the design of synchronous machine is clear. But if you have any doubt or you want any other explanation regarding to the particular topic, you can comment me in my comment box, and as well as you can also message me. Your comments, your messages are always welcome, and I will try my best to resolve all the issues that are created, that are generated in case of a synchronous machine. Now we will start the design of synchronous machine in terms of continuation part of the armature design. Now to start with the selection of number of slots in case of a AC machine, we know that in case of a AC machine, your slots is basically dependent upon your slots is ultimately dependent upon stator slot pitch, and this stator slot pitch is basically equals to YSS, and empirical formula for calculating the number of the stator slots, that is SS is equals to pi d upon YSS. This slot pitch is vary from machine to machine, and ideally its value will lies between 25 mm to 35 mm. But apart from that thing, it will also dependent upon the machine to machine, whether it is a salient pole machine and whether it is a non-salient pole machine. Moreover, for calculating of the stator slots, we also kept in mind that stator slot is equals to QMP, where Q is the value having 2, 3, 4, 5, so on. M is number of phases and P is number of poles. Now in this video, we are see what are the various factors that you should kept in mind for the selection of stator slots in case of a synchronous machine. The very first step will be balanced winding. The number of slots are so selected that a balanced three-phase winding is obtained. Unbalanced winding will lead to generation of space harmonics and overheating. That means if you use a balanced winding in case of stator slot design, then the harmonics will not generate it and the machine is not get overheated. Otherwise, what will be happen? The harmonics will generate in a machine, due to which the machine will come into cogging and crawling condition, and also the temperature of the winding of the machine, which can be reduced to a greater extent. Otherwise, the winding present in the stator slot get damaged due to the overheat. Number two, tooth flux density. The selection of number of slots will lead to narrow tooth resulting into increased tooth flux density beyond the permissible limits. So this tooth flux density should also kept in mind while selection the number of stator slots. Leakage reactance. With less number of slots, the conductors are nearer, leading to the increased leakage flux, and thereby increased leakage reactance. So that means if you have to calculate the number of stator slots in a machine, your leakage reactance, that is will be equal to xd, should also kept in mind for selecting the total number of stator slots. The fourth point is tooth ripple. With the large number of slots, tooth ripple and therefore pulsating losses are also decreased. So based upon that thing, we have another points, that is temperature rise and cost. So selection of too small a number of slots will increase crowding in a conductor, disturbance in a air circulation, and hence developing high internal temperature. Also, a smaller number of slots resulting in saving the labor because less number of coils to wind, insulate, place in the slots and to connect. So these are basically the 5 points that you must kept in mind for the selection of total number of stator slots in case of a synchronous machine. With these all the factors that kept in mind, we can easily design the number of stator slots. So considering all the points, the slots per pole per phase for a salient machine should be taken as 3 to 4, and for turbo alternator it should be selected as 7 to 9 per pole per phase. As I have already discussed you that while selecting the stator slots, the stator slot pitch should also kept in mind. So the stator slot pitch having the different value. For low rating machine, the value will less than 2.5 centimeter. For medium machine, that is machine up to 6 kV, the value will be 4.0 centimeter. And for high value machines, the value will be less than 6.0 centimeter. So these are the three values for the stator slot pitch on which your number of stator slots is ultimately dependent. So once your total number of stator slots can be calculated, it's the time to calculate the turns per phase. The turns per phase can be calculated with the help of EMF equation, and this EMF equation of the alternator says EPH is equals to 4.44 F into phi m into TPH. Hence, your TPH will be equals to EPH upon 4.44 into F into phi into kW. From this we have EPH is equals to per phase voltage, 4.4 is the constant value, phi is frequency, F is flux, and kW is a constant value, that is a winding factor 0.955. So for calculation of number of turns per phase, we are using this EMF equation. Next you have the conductor section. As we are discussing that the total number of conductors in a machine can be given by the formula Z is equal to 60pH, which I have already discussed with you people. Now, number of conductors in a slot we have calculated. We have to calculate the conductor area. So for that thing you have current per phase is given by Q upon V. So Q is equals to in kVA into 10 raised to power 3 upon 3 into EPH, because it is a three-phase machine and EPH will be the per phase voltage. The conductor current IZ is equals to IPH, and this IZ current per conductor is given by IPH upon A, where IPH is current per phase given by the earlier formula and A is the number of parallel paths. Now the cross-sectional area of the conductor, that is AS, is equals to IS upon current density, where current density is given by the formula rho s. and Is is the current density. The suitable value for the current density is assumed, and it has certain advantages and certain disadvantages. For numerical point of view, this current density is a value having 2.5 amperes per mm square, because current density's value is always in mm square. So the advantages of the higher value of current density is reduction in cross sectional area, reduction in weight, reduction in cost, whereas the disadvantages of higher value of current density is increase in resistance, increase in copper losses, increase in temperature rise, reduction in efficiency. So the conductor area is having certain advantages and certain disadvantages. Based upon this thing, higher value is assumed for low machines and small machines. So generally, as I have already explained to you, the value of the current density should be taken as 2.5 amperes per mm square. So usually the value of the current density for the stator winding is taken as 3 to 5 amperes per mm square. Mind it, the value of the current density should always be in amperes per mm square, because the area is always in mm square. Now, quickly coming to the next topic, that is stator slot dimension. Now, up till stage, what we have to do, we have calculate the total number of stator slots. We calculate the total number of conductors. We are calculating conductors per slot. We are calculating the area of the conductor. Now we have to calculate the size of the slot. And this size of the slot is basically called as the slot dimension. Now the slot dimension is given by the formula Wt is equals to phi upon psi SS upon P into Li into 1.8, where this psi is 0.66 the value, that is ratio of polar to the pole pitch, SS stator slots, P is number of poles, Li is length of air gap, phi is flux. Each and every value we have to be calculated previously. The depth of the slot ds is not determined by the space requirement for the copper and insulation. The depth of slot is normally 3 times the width. So firstly, we can calculate the width, and after that we are calculating its depth. In the same, the length of mean turn can be given by the formula LMT is equals to 2L plus 2.5 tau plus 0.6 kV plus 2.2 meter. So based upon that thing, we are calculating the value of length of mean turn. So you can say that by calculating the number of slots, the factors on which this number of slots will dependent, it's having certain advantages and disadvantages. The turns per phase, based upon this turns per phase, we are calculating conductors, and after calculating conductors, we are calculating conductors per phase. After that, the wire or a material can be used for the conductors, that is a cross sectional area of the conductor. When we use the cross sectional area of the conductor, it has certain advantages and disadvantages. We have to calculate the slot dimension. So once this thing can be calculated, it completes the overall design of the armature winding. So here I can conclude that in case of a synchronous machine, the main dimensions include the calculation of diameter and length, how this diameter and length can be separated out by the means of L by tau or by the means of peripheral speed. The main, you can say that design of armature includes turns per phase, number of conductors, stator slots, conductor per slot, number of slots, dimension of slots, and the area of conductor. So these are 5 to 6 points that we are discussing with you about the conductor, the armature design, as well as the main design. In addition to that thing, we are also discussed about the length of air gap, the armature mmf per pole in the armature as well as the field winding. So these all we will cover. I hope you can understand all the concepts behind the main dimensions of a synchronous machine and the armature design of a synchronous machine. You can watch this video. It is a very beneficial for you people. You must watch this video, and after watching this, if you have any doubt related to the armature design, related to the main dimension which I was discussed in my previous video, you can correlate both the videos. First of all, you watch my previous video on the design of synchronous machine, and after that you can watch this video on the design of armature design of the synchronous machine. You can get easy to understand the main dimension design as well as the armature design. So after watching this video, if you have any doubt or if you want to become getting more knowledge about the armature design, you can comment me or message me. The messages and the comments are most welcome to you, as I have already explained to you. So I will try my best to clear your doubts as well as your concepts. So with this, thank you so much for watching this video carefully. In the next video, I am coming with you people with some more design that is related to the armature design, in which we are dealing another components of the armature design. So once again, thank you so much for watching this video carefully. Thank you.